Well, hello everyone. My name is Richard Buswell and I'm a Professor of Building Systems Engineering at Loughborough University in the UK. For the past 15 years or so, I've been involved in 3D concrete printing research, and that's what I'd like to talk to you today about. But before I get into the details of the technology, I'd first like to reflect a little on what I think are some of the drivers for changing or moving to digital fabrication. So I guess the global population is growing at a very fast rate, and we've got a constant effort to improve our health and well-being, and underpinning that, of course, is energy infrastructure and the built environment. We add about 1.5 million people to the global urban population every week, and cities already consume about 75% of the world's resources. So it seems to me there's no other option than to do more with less. And to enable that, we need to challenge the way we do things. So, of course, construction is at the centre of this, and we know that we hopelessly overrun and go over budget on large projects. This is one plot that sort of just maps on a whole range of projects, and you can see those that come in on time under budget right down at that bottom left hand end are very small indeed. In fact, about 98% of projects overrun, and also productivity is flatlined when we compare it to in construction, when we compare it to manufacturing. And we know the challenges. We have skilled labour shortages, our populations are ageing, we've got hazardous working environments for operatives that are undesirable. And with automation, we might hope to start to take the operative away from the hand operations and close contact for those dangerous materials and chemicals. We can increase their productivity by bringing them in to manage machines that are able to work for longer periods of time, producing more products. We can hope to increase quality and reduce the variation in the parts that we make, and hopefully be able to, through automation, be able to better predict the time and cost of components. And this is particularly relevant in construction, where we're talking about long supply chains. We're talking about fitting in with on-site and adapting to changes on-site. So automation allows us to do some of these things. So doing things digitally can be beneficial. 3D concrete printing, which is really at the centre of the talk today, is one of those technologies that could be part of this digital transformation. And it's a really exciting technology because it takes digital models and uses that information to drive digital processes. So in the late 80s and 90s, sort of rapid prototyping was developed, and that was to become additive manufacturing later. So showing here is a video example of a stereolithography process that uses an ultraviolet sensitive resin and a laser to activate the liquid and turn it solid. So basically we have a digital model of the component we want. We then slice that into a number of layers, and on each layer we can define the areas that are required to be solid and the areas that are not. And each of those layers is sent to the machine that controls, in this case, the laser, but it might be that where the material is deposited or where a binder is deposited for powdered material. And then each layer is consecutively bonded together to form a complete three-dimensional object. And there's particular advantages with this, and in prototyping, what it enabled was the fact that you didn't need the mould anymore to create your end-use part. And so all of the time and effort involved in making the mould for forming the functional material for the prototype was removed. And hence, although the manufacturing itself wasn't rapid, if you looked at the time to take the mould to the time of your finished part, that was shortened significantly, and hence rapid prototyping. But subsequently, with developments in materials and more exploration into the material properties, then the same processes can be applied to manufacturing parts directly for end use, and hence rapid prototyping sort of evolved into what we're more familiar with, which is rapid manufacturing. And there are many examples of rapid manufacturing where sort of design freedom and low volume production has significant importance. And these are forming the basis and underpinning many businesses across many sectors. And there are a number of advantages that are well known. So we get affordable, flexible production runs, and these because you've got freedom of geometry, you get customization for free. And of course, this lends itself to producing one-off parts and customized parts for value added. You can print on demand. You've got control over how long, simulation drives how long you can predict parts will take to manufacture. This enables you to do just-in-time manufacture. You get digital catalogues of parts. You don't have to store anything physical. You can use it to shorten lead-in times because you're taking this moulding, this preparation time out. The elimination of tooling reduces materials and material waste streams. And of course, the freedom of geometry allows you to be more efficient with the use of material itself, all of which benefits. And so the question is here, this is well known in manufacturing. So really, why can't we do the same thing in construction? So a little bit further down the road from those initial rapid prototyping forays were the digital fabrication in concrete, where we were using CNC processes to mill out polystyrene molds to generate unique parts. And the image here is Giri Zollhof Towers, which had 355 different panels that were enabled through that digital manufacturing. And it was really the early 2000s when the first large-scale additive processes came on the scale. The seminal work of Joe Pena in 1997 produced the first autoclaved part for the concrete block that was additively manufactured. But the first sort of construction level stuff was contour crafting, which is well known from Baruch Kroshnowitz at University of Southern California. And at about the same time, Enrico Dini and D-Shape in Italy were looking at a printer that used a sand particle bed based approach. And a little bit later was our work at Loughborough University, when we looked at sort of offsite concrete extrusion, closely followed by many others. And in fact, since then, there's been a huge growth in the interest in the technology. This was something we put together for our paper we did with colleagues run up to 2018. And I think from there, we go from strength to strength. We did a survey, an internet survey last year, and we were looking for organisations that were offering commercial 3D printing services, and we found about 35 commercial organisations, which is significant. They're spread internationally. For sure, these are not all of the ones out there, but the interest in manufacture is certainly increasing. We also, a little earlier this year, part of British Precast Week in the UK, we did a presentation on 3D concrete printing technology, and we also used that to poll some of the participants. We had about 65 people there, I think 65 organisations, and we asked them a number of questions, and subsequently we talked to a couple of manufacturers as well, just to sort of understand where the industry was as it relates to sort of off-site manufacture of concrete parts. And I think what was really encouraging, about 80% of the people who we polled as part of that seminar saw that 3D concrete printing in the future of their business. What was interesting was that manufacturers were keen to protect or increase their market share, and potentially branching out into new product offerings that they didn't currently do, sort of diversify what their manufacturing was. Also, uncertainty over importing certain products as well from overseas and having to sort of repatriate that manufacturing was also leading to interest. One of the issues that we did come up was the fact that because we have craft-based, we know that experts and highly skilled craftspeople do superb work, but they're few and far between. And what can happen is operatives can sort of interfere with established processes and procedures, all trying to do the job a little bit better. And this can cause problems with consistency in product manufacture. And so one of the interesting things was that people were seeing the opportunities to have sort of locked down material supply chains, digital processes a bit sealed up. The operatives would become a step away from some of the important parts of the process, and that actually would take the uncertainty out of product manufacture. It was also seen as a benefit, again reducing waste from products that need to be scrapped through underperforming materials. And then there was also some general sort of stories about productivity needing to be leaner, continuing to drive for digital manufacturing, etc. But all very positive messages indeed. So let's have a brief look at 3D printing technology. Really, I'll just give an overview of the types of systems that are out there. Recently undertook pulling together a classification framework with international colleagues as part of the Rylam Technical Committee on the digital fabrication of cement-based materials, which is just completed. In fact, the report from that technical committee is with the publishers at the moment, and that will be out very soon. So if you're interested, then please keep an eye out for that. This is both published and is part of that technical report. But we were interested in looking at a way of helping our community frame and talk about the differences between digital fabrication technologies, and we came up with this framework. Of interest here today is the section that relates to the additive manufacturing. So the differences being we sort of form stuff, i.e. cast them. We can subtractively manufacture things, i.e. we take away material from the solid blocks like milling or turning, or we do them additively where we're selectively depositing material or solidifying it. And if we zoom in a little bit, then we have these three categories where particle bed binding. So these we aligned with the ISO standard for additive manufacture in terms of the terminology, with the exception of particle bed binding, which we decided to depart from a little bit. But essentially, particle bed binding is we've got a granular material that we are sticking together with a binder selectively. Material extrusion, we are extruding a filament of material and placing that where we want. And then material jetting is effectively like a shotcrete approach, where we're spraying concrete in a layer by layer approach. There are obviously room for new methods to come in, and one such one is what's being called injection concrete printing. It's really an extension of material extrusion. It actually extrudes the concrete material, but it does so in a suspension that's of similar density, so that you can actually print in 3 dimensions. And I can explain, got an image to explain that in a minute. So particle bed binding, these images are the D-shape process, and effectively here what we're trying to do is you are laying out sand in sheets of about 10 millimeters thick, and onto that sheet you're then depositing a binder, as you can see that in the right hand image. You can see the wet patches where the binder has gone. You then push another sheet of material over the top and bind again, and then those layers bind together, and you effectively end up with your complete component caked in loose sand, and that sand has to be removed. But the advantage of that sand is that it provides natural support, so it gives you a lot of freedom for producing overhangs and interesting shapes. It's all done on a large gantry system. There are advances being made in using larger aggregates as part of this to make more of a concrete, and also in terms of orientation. So there are systems that have been positioned, sort of almost rotated through 90 degrees, and the build face, rather than being horizontal, is 45 degrees, and then you can build out horizontally to make far longer components. Material extrusion is by far the most common approach. Here we're using mixed materials, either batch mixed or delivered through a continuous mixing system, and they are pumped with fairly standard pumping equipment to a nozzle that's mounted on the end of a robot to allow positioning. You can control the sort of rheology of the material and the setting of the material with the injection of admixtures at the nozzle. So some systems will just deposit the material directly. Some systems will have this dynamic mixing approach where you can adjust additives at the nozzle as well. The two principal approaches, but they're fundamentally the same, doing the same thing. The positioning systems are generally either gantries or robotics, but there are other systems around. And most of the large scale stuff has been done. It's also, many applications are done off-site for manufacturing parts, but also on-site for looking at doing sort of buildings in situ. And one of the main things that we've been looking for at Loughborough is we're working actually with John Provis at the team at Sheffield and Susan Burnell at Leeds, as well as part of one of our current UKRI grants that we're looking at concrete printing materials and hardened properties. We're doing that in collaboration with Manchester University as well, but this is sort of extending the work we started back in the mid 2000s. Material jetting is a really interesting application. So it's sort of similar in some ways to the extrusion, in that we're selectively placing the material, but here, rather than extruding a filament, we're jetting the material sort of onto itself. Again, it's different from shotcrete, because shotcrete you're firing the material against a hard substrate, and here you're actually firing it onto itself. One of the nice things about the approach is that you can actually quite readily encapsulate reinforcement with spray concrete, which allows you certain advantages over the extrusion-based method. And just an image showing this injection printing method. So this uses sort of a gel that's a very similar density to the concrete itself. So when the positioning system sort of moves through the gel, extruding the material, it's actually held where it's laid, and this allows you to do some interesting and novel things with it. And there have been some quite large parts been made. What's really interesting is that all of these methods actually have commercial offerings. They're available. There are organisations out there that are, offering products and services based around all of these systems. So let's have a look at applications and what's being done. So I've got a range here. There are too many to include, but I've just picked a few that have some sort of, just to make some highlight points through this. This one is claimed to be the world's largest building. It was built by Apiscore. So this is 9.5 meters high. You can Google and find the finished image. I thought I'd do one sort of half in construction for this, but it's about 640 square meters. They used a gypsum-based material for this. It's printed in Dubai, and I think this is interesting because when you try to print in situ, there is a size issue. Now, there are some approaches which use a large gantry that's larger than the building that you're trying to print, in order that you can get all the walls in. So in there, you're quite interested in trying to generate more height, because obviously you're constrained by the gantry. So in order to get the most out of the overhead from positioning the gantry, then the higher the building, the better. But the approach that Apiscore has is slightly different. Is they have one machine which can actually sit inside the footprint of the building, and then that can be moved to different parts of the building, and it's sequentially moved around in order to print all of the parts. Then the floors are laid in, and then the machine's dropped in on top of the floor to continue the walls up. So I think, again, there are interesting innovations and different approaches for delivering on-site manufacturing, all of which have benefits. This was a really interesting piece of work by Kobod in Copenhagen, who are doing some great work and regularly advertising. They've been really doing well, pioneering getting buildings actually built with their printers. So this is a collaboration between General Electric and Lafarge Holcim that they did in 2019. I was actually lucky enough to see this, or part of it being manufactured in their facility. But it's a 10-meter high foot boot for a wind turbine tower. So the manufacture of wind turbines is limited due to transportation lengths, and this limits the height at which the wind turbines can be installed. And obviously, if you can push those wind turbines higher, you can get more efficient use. So the idea behind this is that you can actually on-site print a boot to boost the height of the wind turbine, and that can be tailored to fit. The idea of this, it would actually be post-tensioned against the footing that would be in the ground. So again, really big stuff being manufactured, and it's not just buildings and benches, but actually there's lots of forays into understanding where it can be used to deliver large bits of infrastructure. And this was a 150 meter long revetment wall built in China. So again, this different approach. This used concrete printing and precast, conventional precast, to make a slab, which the concrete printed sections were then printed on, and then those sections were then moved to site, put into place to create this revetment wall. So again, I think this is interesting because it's not just concrete printing that we're seeing, but it's concrete printing and those processes being used in combination with traditional and other methods that are ordered to deliver benefits. So it's not just about the pureness of the technology, but it's just about new approaches to manufacturing and production, which I think is really exciting. There are lots of bridges. This was just a recent one I thought would use. It's just been recently put up in Venice, collaboration with ETH Zurich, Zaha Hadid, and Incremental 3D. Again, this is nice. This uses design and the flexibility of being able to produce 3D concrete printed parts that actually interlock together. So effectively, this is a masonry structure with no reinforcement. So it was designed to be self-supporting, and the installation, and you can see the pictures on Zaha Hadid's website. They've got a set of these if you're interested to look at these. But there's a piece of the formwork is set up. The pieces are placed on the formwork until it's all locked together, and the formwork removed, and it is there sit in situ. So again, the geometry of the parts is enabled at a cost-effective way through concrete printing, and you can design in different ways. So this can be disassembled and moved at the end of life, for example. And there are new ways to interact with design as well. So Mobot are a startup company looking at creating bespoke concrete chambers. So they also using a sprayed technology. They can incorporate reinforcement, and their market pitch is to produce inspection chambers. But what's really interesting is they can also, on their website, they have access to a parametric design tool where you can reconfigure your boxes, and that's linked through to the actual manufacturing process as well. And of course, that computer control then can schedule the manufacturing, production and delivery of your components sort of on demand. There are numbers of lots of interesting facades and walls. Again, the freedom of geometry doesn't just allow you to do architectural things, but it allows you to rethink things in different ways, i.e. make walls readily accepting of plants growth, etc. And there's also lots of interest in how we can embed in additional function in the parts. If we've got the control of geometry, can we deliver more function with the component so that we actually get value added. We do something more than just a conventional cast product. And for sure, this is a really interesting topic. And actually, we're at Loughborough, we've been focusing on the production of panels that could be sort of facades as well. And there are many architectural components. Again, I've just picked a few of the really nice sort of furniture orientated ones. We've got X-Tree and Studio 7.5 did their woven bench at the top there, which is really nice. So there they were exploiting the sort of intrinsic material characteristics through clever control to deliver aesthetic patterns that are unique to the process, and hence have value. And also, lots of designer collaboration. So, the digital aspect of this really unlocks the access for designers, and as they understand how to use the process, then you start to get some really innovative new designs that you just simply wouldn't do with conventional processes. So not only ones that would be expensive to do, but actually that are inspired by the nature of the process. I think that centre run of benches by Philips and Additive and Incremental 3D are particularly good for that. And also large organisations are coming together, and Picus and Seeker are examples of that, and they produce that really nice sort of curved bench item down there. But again, I think what's interesting is there's lots of forays out into different products. There's a lot being done with architectural items, and principally I think this is because these applications are very much the tech is ready to produce these applications, where those geometries have ready value to designers to produce different things. And you've got low volumes, and sort of customization is sort of value added. All of those benefits are perhaps what's driving these the production of these sorts of things as a first introduction into the market, which I think will only grow outwards. And looking at the applications, when we did our internet survey of the organisations that were offering some sorts of services, they're broadly split into two halves. Half of which was doing on-site construction. So this is the production of walls for buildings, pretty much. And the other half is looking at off-site manufacture, generating products. And of those, there's a whole range from furniture, cladding panels, chambers, other things. So the image there is of replacement coral reef. So, being able to manufacture habitats that would be good for marine life. And so what of the future? Well, since we started in the mid-2000s, things have come a long way very, very quickly. We've made great advances since the seminal paper we did on the material properties sort of for printing concrete that we published in 2012. And since the materials community has come on board, the understanding has increased tremendously, and I think you can just see the standard of the quality of the components that are being made worldwide is really, really testament to that. But I think moving forward, the emphasis is firmly going to be on the measurement and control of these wet properties, and in making sure that we have reliable properties that enable builds to be accomplished without fault and failure. We trying to measure things in an automated way so that we can then build in these measurements to make processes operate without the need for human intervention for checking is still not quite there, and we absolutely need to move in that direction in order to get this sort of lights out push button operation that we really want to see with the technologies. One of the approaches has been pioneered by colleagues in Naval Laboratories, which is near Ecole de Paris Tech, or or now as it's Gustave Eiffel University. But Nicolas de Colombier recently completed his PhD there. He's now working for Extrusion, and his supervisors, Jean-Francois Caron and other colleagues, developed this slug test, which is a way of trying to look at the yield stress, measure the yield stress of the material. And we want to know that because the yield stress of the material is critical when you're using extrusion-based concrete printing, because it affects the formation of the filament. So we need to make sure that's absolutely right in order to get the builds that we want. And so this was a really novel way of doing that. But yeah, there are. This is really important and is actually forming these quality control measures are forming the basis of a new RILAM technical committee led by Nicolas Rousseau and Dirk Loki, who are where we're going to be looking at understanding more about how these processes can be deployed. Reinforcement is also a big issue. We know that the 3D concrete printed material is anisotropic, and we are still understanding the reasons and the mechanisms for this. There's been some good work done recently, which has been sort of identifying the little voids and air gaps that happen when we start to lay filaments together. Obviously, because we're laying filaments, again, particularly with extrusion, there's opportunities for faults to occur between those, and they can change the properties of the material. But we also need to understand how we can incorporate reinforcement into the printed material as well to extend the applications. There's a very good review paper led by Victor Mecher-Turenne at Dresden, which the reference is there if you're interested, where they've looked at all of the publications on the various approaches to reinforcement. And so that's a good read. And Victor and Freek Bos of Eindhoven are also leading a parallel RILAM committee on quality control, measurement and assessment for concrete materials and structures, which is also be picking up this work and trying to understand how we can evaluate these things better. Clearly, we have to understand how the materials perform and how to get them to perform consistently in order to be able to create design tools and design structures using 3D concrete printing. It's going to be a super important part of the future work. And dimensions, tolerances. We're particularly interested in this at Loughborough as well. Much of the focus has been on producing systems that work and can make things, but now the community is starting to look a bit more about how accurately we can make things. And there's lots of applications of light-based metrology systems, doing interrogating printed parts, understanding the deviations from the digital models that we want, and understanding how we can achieve this is really important again to enable design, because we're effectively positioning a wet material that's having to support under itself weight, and how that's positioned and what happens to the material and the way it's loaded will all cause slight deviations from a very exacting CAD model. And we need to understand what those differences are, again, if we're to understand what tolerances we can manufacture to reliably to fit in with other parts. So we were more interested in looking at systematic ways of improving that. And some of the work we're doing at Loughborough, we're quite interested in looking at offsite hybrid methods. So acknowledging that printing can get us close to what we want, and in many applications it is good enough as it is extruded to be fit for purpose. But there are times when the very nature of extruding the material and the surface is not quite good enough. And for those applications, we've been looking at printing and using subtractive milling. So we get the geometric form that we want with the printing. So we've got freedom of where we can place the material. But by looking at how we can apply subtractive methods of milling, we're able to then much more accurately trim the surfaces to tolerances, and very roughly we're talking about taking maybe plus or minus 10 millimeters down to plus or minus 1 millimeter. And I think this is really important for assemblies that need to fit together, and for looking at how you can make parts that fit in with other parts of buildings. Now, this work is part of UK funded research from the Industrial Strategy. That cycle completes March next year, so there will be a little bit more of this coming out of Loughborough in the coming months. So I'd just like to finish off really by mentioning a couple of activities. So in the US, ACI is looking at the printing of cementitious materials, and there's a group there that are trying to bring together a vehicle for dissemination and discussion of additive manufacturing methods. Rylam is leading, or has led, TC276, which was the initial technical committee that's now closed, looking at digital fabrication. Again, the state-of-the-art report is going to be published very soon from that, and it's also led on to the formation of 2 new technical committees, performance requirements and the testing of fresh printable cement-based materials, led by Nicholas and Dirk, and the assessment of additive manufactured materials and structures, which is led by Freak and Victor. And finally, Digital Concrete 2022 is going to be held on the 27th to 29th inclusive, June next year in Loughborough. It was at ETH in 2018, and it was online in Eindhoven on 2020 due to the pandemic. So this will be the first time in 4 years the community's had a chance to come together. So it's set to be a really great event, and we're super privileged and happy to be hosting this. So the abstracts, the call for abstracts is out. We've extended this a little bit to mid-October, but if you want to go to the website, please use the link that's there, www.digitalconcrete2022.com, and you can get the details of that, and please keep your eye on the website that will be developing in the coming weeks. And also, if your organisation is interested in sponsoring the event, then by all means, please contact me. And I hope to see many of you next year at the Digital Concrete event, where we can talk about all of these issues more. And I hope you enjoyed my presentation. Thank you very much for your attention.